Well, good afternoon. It's going to be hard to follow that session over lunch, but welcome back. My name is Gaudenz Danuser. I'm the founding chair of the Lyda Hill Department of Bioinformatics at UT Southwestern Medical Center, and I also hold the Patrick E. Haggerty Distinguished Chair in Basic Biomedical Science. And after last night's ceremony, I have to say I'm one of these 300 plus CPRIT recruits that were made over the last 15 years. So I had also the pleasure to be serving as the science co-chair for the TAMEST 2024 annual conference. And for this science session, I'm very excited that we have now 3 speakers who will showcase how recent advances in AI drive progress in scientific discovery. We will hear how AI enables the development of predictive models in physics and the life sciences, how AI enables the identification of the link between genome sequences and the biological functions they promote, and then how we can use AI to turn the table and synthesize sequences with new functions. And finally, we will hear how AI intersects with neuroscience to generate ever deeper understanding of the mechanisms that underlie human and alternative forms of intelligence, as we heard this morning already. After a short break, we will then pivot away from AI and hear from the 2 science recipients of this year's Edith and Peter O'Donnell Awards. I am now pleased to welcome our first speaker, Dr. Petros Koumoutsakos. He is the Herbert S. Winokur Junior Professor of Engineering and Applied Sciences and Area Chair for Applied Mathematics at Harvard University. Dr. Koumoutsakos is a member of the National Academy of Engineering. As was said this morning, you have the full bios of all our speakers online on the TAMEST website. So after Dr. Koumoutsakos has concluded his presentation, we'll have, again, as this morning, a few minutes for questions from the audience. Please join me in welcoming Dr. Koumoutsakos.
Thank you. Good afternoon, everybody. It's a great pleasure to be here. It's a great pleasure also to be introduced by a fellow Swiss citizen, Gaudenz. I'm also Swiss, despite my name. I'm also Greek, as you will recognize by my accent. So I would like to tell you about AI and scientific computing, and I will paraphrase a famous statement that there's plenty of room in the bottom by Feynman to talk about how there is great opportunities between AI and scientific computing. So the previous panel talked about the human fabric. So we gather together and we gather in such conferences. And this is something that we have been doing for about 2,500 years. And the reason that we do that is because we are interested in pursuing the truth. So seeking the truth was something which was central to the dogma of the Greek philosophy. So one of the people in there is Plato, and maybe many of you know this parabola of the cave, the allegory of the cave, and the idea is that all of us, we are somehow chained in a cave, and what we see in front of us is not actually the truth, but are shadows of the truth. So we spend our time not watching the real thing, but watching what we see in front of us, and then we spend the time arguing about what is it that we saw. We say this was a dog, an animal, or a pet, and then according to this allegory of the cave, somehow one of us gets released, gets out and sees the world, and so finds out that there is blue skies and 3-dimensional objects and everything. And the continuation of this parabola is he goes back to tell the others, and as it is the Greek tradition, they fight among themselves about who's right. So the pursuit of the truth is something that we have been conducting with many different ways. One of these ways is to look at the core of nature. So we're building these wonderful machines at CERN, where we're looking at what are the components of the atoms. And at the same time, there is another way that we look at things, not by experiments, but by using computers. So here is a personal history of the different computers that I touched in my life, including the Lumi that was mentioned earlier. So what has been amazing in this journey is that there is no other equipment, I think, that has seen a magnification of about 1 trillion x during a lifetime of a person. So this is a wonderful opportunity. So what is it that we do with that? So we go and we investigate, for example, how water propagates inside carbon nanotubes. I will talk about this. This is propagation of blood inside microfluidic devices to find circulating tumor cells. And I will talk also about macroscale phenomena like shock bubble interactions that we are simulating. So one of the biggest simulations ever made was actually an effort to try to complement experimental efforts in detecting circulating tumor cells. This was in collaboration with a group of Mehmet Toner at the Harvard Medical School. Mehmet, he came up with a device where you pass the blood through these different posts, and if you have cells of different size, in this particular case, you have a white blood cell that is being separated by the red blood cells, that they have a different ratio. By using some fluid mechanics principles, he was able to separate. Now, when he was building these things, he did not know how to design it. There was a lot of ad hoc methods. So we collaborated, and we actually did a one-to-one simulation of their device, and then we tried to understand how their device is separating the blood from the larger structures. We were able to do optimization. Now, the problem with the simulation that is involving actually 1 trillion computational elements, and it's not easy to be repeated to help very much the designs. We also do other things. We are interested in bubbly flows. Usually people who do bubbles, they will do a few tenths. We were able to do tens of thousands by coming up with interesting numerical methods that are able to capture these bubbles. I would like to emphasize that this is not graphics. This is actually physics. And then we can take also these methods, and the same way that you do waves, you can also do bubbles in microfluidic devices. Finally, moving on to something that I will talk a little bit more today is I will talk about turbulence. So we talked about the flow around aircraft wings. What you see here is a tiny, tiny portion of what's happening inside of about 1 millimeter cube over an airplane wing. There is all this beautiful structure of turbulence. There is this wall turbulence, and the question is, this is one of the open problems in physics, what does it take to calculate them? So people have been calculating turbulence over the years, and as the flops of the computers are increasing, that you see here on the left, then what we can do is we can do more and more complex flows. There is a number that is called the Reynolds number that says how fast things are going, and here you have to observe that if you want to do a real aircraft, you have to go to 10 to the 7, and what we are able to do is much lower numbers of about 5,000. And perhaps what is the advantage is what we were able to do before, let's say, overnight. Now we do it in less than a minute. And what we were able to do over months, we are doing it now, again, very, very fast. But we are far away from that. So how many elements do you need in order to compute a turbulent flow? Here are some estimates that people have done. So you see here that if you take this 10 to the 7 and you exponentiate it to 2.6, we are very far away from that. But there is hope in coming up with models. That's what is M here, is wall-modeled large eddy simulations, where there is hope that we can resolve these flows. Now, solving for flows is a very interesting exercise. It's something that is also relevant not only for aerodynamics, but for other systems. And there is, of course, certain challenges, like chaotic dynamics, expensive to simulate, challenging to forecast. So how can we design fast methods? There are existing ways of how to do this. They're not very satisfying, and there is a lot of room where we can improve on that. Now, this has been the computer's perspective of scientific computing, people like myself who take computers and try to solve equations. I think the public became more aware of computers when the Deep Blue beat Kasparov. In fact, actually, there is an interesting anecdote that beat Kasparov because of a bug, but that's another story. But without a bug, it beat, as it was mentioned earlier, humans in the game of Go, and I guess maybe you probably know that computers are better at playing poker at Texas Hold'em. So that's it seems to be a very sophisticated capability. So question is, the physics-based models are computationally expensive. Can AI help? Everybody talks about AI today, and how? So this is a question that concerned me for the past 30 years. I wrote my first papers, actually, application of fluid mechanics, application of machine learning to fluid mechanics, back in 1997. I was not able to publish it anywhere except in the proceedings of the Center for Turbulence Research at Stanford University. And then I wrote another review, more recently, 2020, that has over 2,000 citations. And the numbers that you see here, these are not the citation, these are the flops of the computers that we have over the years. And you can see what we were facing back in the early days of trying to do machine learning for science, what it would take today about 2-3 minutes to compute. Back then, it would take a year in a supercomputer. So now we can think different. So if I learned something from this journey, and I'll give you some examples of that, is that if you have these two fields of the scientific computing, which is for simulation, and artificial intelligence, the lessons I learned is that on the one side, you have mathematics. On the other side, you have something that's called architectures, and I will show that. You have statistics versus determinism and exactness, which is something scientific computing was always pursuing. We were always pursuing understanding, but in AI, you don't always have to understand. Provided you achieve your goal and you achieve it fast, then you're doing a good job. And I think where there is plenty of room is when you combine the best of this world and you develop something that I call algorithmic alloys. So I'd like to show you some of these alloys. So the first one is called learning the effective dynamics of complex systems. So just to tell you the difference between mathematics and architecture, if you have some data and you want to find out what is the dominant mode in the data, you can do something that is least squares or proper orthogonal decomposition or PCA. And now if you have this formula, you formulate a covariance matrix. You have to find eigenvalues and eigenvectors. This is a linear operation. If you are not happy with that, how do you develop a nonlinear form of that? That can be very difficult. But if you adopt the architecture point of view, that is, you adopt a neural network, and you say the input and the output have to be the same, and in between I have some linear activation functions, then if I find out what are these linear activation functions by the weights of the linear activation functions by minimizing this number over here, then we find out the eigenvectors that you can also find from here. But of course now, it's very easy to take these linear activation functions, make them nonlinear, and try to do better than what this least square does. So actually, we did that back about 20 plus years ago. We actually, I think, were the first who did deep neural networks. We started adding layers until we get some kind of an answer. So this is reconstruction of a vorticity field from a turbulent flow. This is what was the state of the art back then, and this is what the neural nets gave us. Now, moving forward, there has been a lot of adventures in between. So now we are interested to find out if actually we can do something beyond compressing the data. Can we forecast with neural networks? So here's the idea. I will collect some data. I will train my neural net, and then I will try to see if I can predict. Now, in order to verify that what I predict actually is something that I can test my algorithms, I can take a partial differential equation. I can do the classical discretization, and therefore, I have always the answer to my predictions by solving this equation very accurately. So the question is, what if I take some partial data from these simulations over here, some early times, this is time, this is space, and then I use machine learning, state-of-the-art recurrent neural networks and transformers and what have you to try to predict what happens in the future. The way we do that is we actually take the real data, and for reasons that I don't have had time to explain, we actually compress the data, and then we train the algorithms in a short-term history with this data, and then we want to see what can happen in the future. How far in the future can we go? So we use these LSTMs. As I said, transformers don't give very different results, and then in an autoregressive way, we are looking at what can come out in the future. And what you can guess is right after the training, we are predicting very well. As the time goes on, We are still doing OK. We're still doing OK. And at some point, recurrent neural nets and every other machine learning algorithm that we faced actually fails, and they cannot predict in the long, distant future. In fact, you can see that as we increase the chaoticity of the flow, this is actually a number that says how chaotic the flow is. The higher the chaoticity, the sooner that we're going to fail. So there is a point to make here that these methods, machine learning methods, are not yet ready to replace the solutions that we do by solving numerically partial differential equations. Now, can we do something with that? Can we fix that? So here's an idea of how you can fix that. The idea of how to fix that is what we call learning effective dynamics. There's several other people who have worked on this concept. One of them is Yannis Kevrekidis, who came up with the equation-free framework. This idea is inspired on his work. The idea is that if you do a few steps in a simulation and you acquire training data that you can project into some kind of a latent space, then the recurrent neural nets can propagate, and then whenever you need to go back, you go back through a decoder. You're doing a forward and an inverse operation to go to the latent space, and by doing that, you actually can take advantage of however long you can predict accurately in the latent space, and then you need to bootstrap yourself back to the full simulations, and you go back with the decoders. All these things, this idea was there before. What was new here was actually to use RNN's LSTM for propagation in the latent space because it allows you to get memory, and also to use clever decoders, stochastic decoders, to go back out into the full-scale dynamics. So how good is this, and what lessons can we learn? If you take, again, this equation, the Koumoutsakos-Iwasinski, and now we do this game, and in fact, I'm going to stay here for the show to showcase something. I will stay only in the latent space. So you will see if I predict only in the latent space, I'm orders of magnitude faster than my reference solution. But when I project this latent space back out to the full dynamics, you will notice a difference between this one and this one. Now, this difference shows you that you cannot exactly get the same thing, but if you look at something else, which is more coarse-grained statistics, like the phase space or the first and the second derivative of the quantity of interest, you find an excellent agreement between these two calculations. And again, depending how much you use the latent space versus the full dynamics, you can be very, very fast. We repeated this to do flow around a cylinder at Reynolds number of 100, and we got some really good results. Now, the problem is that everybody who does machine learning does Reynolds number at 100, and then you have to question this person, what happens at Reynolds number of 1,000 when the flow becomes more chaotic? So I question ourselves on that, and I show you from this that we start to fail. We are not able to predict as good as we could before. But now we start to learn something, and what we learn is that the place where we make the highest error is where the physics are more dominant, and in the case of black body flows, the physics of vorticity production are happening around the body. We have taken this thing, we have fixed it, we can do higher Reynolds numbers, we can do molecules, and so on, but I would like to give you a message out of this exercise, and the message from this exercise can be better described by these simulations that they were done by Google, that indeed we can be able to predict certain statistics about what would happen in the future. But at least with the current technology and the current state of the art, if you want to predict a turbulent flow like this one, this is a high Reynolds number flow, up to 100,000 around a cylinder, you need techniques that go beyond machine learning, and we better keep teaching our students how to compute and how to program and how to do numerical methods to be able to keep understanding. I'd like to show you one more place where classical computing classes with machine learning. So there is a big effort about using neural networks in everything. So one place where people use neural networks is to do inverse problems for PDs. So what is a forward problem? You have a model, you run it forward, you get data. Now, if you have data, can you go back and produce a model? One way to do that is by solving the PDE using neural networks. The idea is you take the solution and you write it as a neural net. And then this is a technology that people know it as physics-informed neural networks. This is actually an old idea that appeared in many places for the last 30 years. But what was new, it was actually when it appeared here, they used the latest and greatest ways of taking gradients. The method works. So if you take the Koumoutsakos-Wasinski, you can solve this. You put the function, the physics, as a loss function, and you solve it, and eventually you can get the solution. Sometimes you cannot get the solution. But what was interesting about this method is that actually, if you have data, you can use the data as penalty terms, and then these penalty terms can actually go into the loss function, so you can do a very fast way of assimilating the data. Now, there's something else, and this is a method we propose. Instead of using neural networks, you take advantage of what people have been doing for decades, of taking the equation, and instead of using a neural net to discretize the solution, you use the classical discretization, and then instead of solving forward the solution, you're doing the same thing as the neural nets do, or the pins, where you are solving for an inverse problem. You can take advantage of all the methodologies, and then, again, this is not a new thing either. There are several people who thought about that before. It's just that we are using the latest way of taking gradients and automatic differentiation. So what's the difference between the two? Should you use the classical methods, or should you use pins in order to solve inverse problems that involve partial differential equations? So this is the two different ways. Let's take a one-dimensional equation. You can see that the two methods give you more or less the same result. Now, as it turns out, if you look at the error more or less is the same. But now where it becomes very, very different is you look at the computational cost, and you find out that this method that I just presented to you is hundreds of thousands of times faster than what you can do with neural nets. So we should be using machine learning, but we should be critical, and we should be also looking to do fair comparisons with existing and other methodologies. You can do inverse problems with this methodology. You give me some data, and I can infer what is this quantity here. We are also looking into heat. You have some temperature measurements, and I tell you what is the particular material that you're doing that. Again, we're doing it always faster than other techniques. You can also give me some velocity fields around the body, and I can tell you where the body is. But there is another application that perhaps applies or is interesting to those of you who are interested in cancer radiotherapy. We more recently applied this technique into multimodal data from tumors. And then what you do there is you get some features, you segment, you find the metabolic map. And usually what people can do in a forward way, they take an equation, they fix certain parameters or infer the parameters, and then you get pictures like this about the progression of the tumor. If you do it in the context of the Odile, this is unpublished data, you take these equations, you get whatever data you have, you form the discrete loss, and then you solve the inverse problem. And now when you do that, this is work with people at the University of Zurich and the Technical University of Munich. The people who do the standard plan of radiotherapy, a way to see what is the standard plan. You visualize the tumor, and you take 1.5 centimeters around, and then you eliminate, you do radiotherapy to that part of the tumor, but then you see where does the tumor come back. So this is real data from patients, and we saw that if you use the same volume, but you discover this volume not by the standard way, but by using gliodil, you would have had higher coverage. Coverage is a way of saying that this particular therapy would have been more effective. So this is an invitation to people who work in this field to try out this method and to see that perhaps one can do clinical studies by following this particular way. We find that it is better than the classical way, at least on this coverage metric in many, many situations. I'd like to close with a last alloy, which is actually the most exciting for me. So there is a concept called reinforcement learning, which comes actually from the animal world, and there is a lot of tradition of that at Harvard by someone called Bruce Skinner.
The two pigeons are at either end of a small ping-pong table. One pigeon pecks the ball as it comes toward him and knocks it toward the other pigeon. Other pigeon pecks the ball back across the table. If it goes past one pigeon, the other pigeon can eat, and if it goes the other way, the other pigeon eats. So that there is a real, it's a real game.
This is what
pigeon,
Bruce Skinner was doing at Harvard, training pigeons. And can you imagine what was the application? Why was he training pigeons? So pigeons were supposed to be pilots inside missiles. And so you will train the pigeons whenever they see a particular landscape to peck on a button, and then the missile will go down. You can read all about that in this MIT review. And now, what is this reinforcement learning? Reinforcement learning is you interact with your environment, and you have some kind of a mathematical formula that you use here in order to infer a policy of how to act to maximize a certain reward. Reinforcement learning is something that people have used a lot in order to do all these successes of machine learning. Actually, a lot of these things involve reinforcement learning to play games and so forth. One place that I use it was to study fish schooling. So I wanted to understand why fish school. Is it because they like each other? Is there an energetic benefit why they do that? And the other thing that I was very much interested in is what can we learn from this process of figuring out fish schooling? Can we use it, for example, in other places where you have turbines interacting with each other? You can see that if you place turbines behind each other, that's what this thing shows, you have a limited load. So is there a better arrangement that you can place these things? And finally, maybe you can have bionic and real fish swim together. And this is from a children's book that I stole from my kids. Now, what you can do is you can go out, actually, and do simulations of this kind. This is a historic simulation again, because it uses trillions of computational elements. It involves about 400 interacting swimmers, Reynolds number 5,000 for each one of them. Has been running for many, many weeks at LUMI supercomputer, but what you see here is there is no control, and then when you put all these swimmers and you give them a gate, they start to diverge, they start to collide. So can we teach them to swim together? So we use reinforcement learning to do that, and we taught them to swim efficiently. So here it is, a reinforcement learning acting on two swimmers. This one down here does its job, and this one wants to swim effectively. So it finds out in an automated way, no human intervention, that the best way to swim efficiently is to do what actually bikers do by going one behind the other in a peloton formation and to exploit all the vorticity that you have in the wake. When they actually do that, they find some beautiful fluid mechanics of how to harness the vorticity that we would not have been able to gather otherwise. It's done in an automated way. We get a 30% efficiency, and then we get some beautiful fluid mechanics when we extend these technologies to 3 dimensions and find there how fish in different formations can swim together. This thing, we have taken it and interact with experimentalists. This is Maury Garib from Caltech, to do drones and to do other things about things to move in an optimal way inside real fields. And also, we have been putting little robots. This is a magnetic robot. It's an artificial bacteria flagella that we are driving it with a magnet and reinforcement learning, and we guide it towards the center where possibly a circulating tumor cell may exist. Last but not least, we have been using reinforcement learning to do one more thing, which is very, very different than control, and this is to replace heuristics that humans use a lot in order to solve equations. So every plane and every car these days is designed by the following way. You take the equations, you cannot solve them, you average them, and then you have some terms on the right-hand side that you model. We came up with the idea that this model can be derived in an automated fashion by reinforcement learning using limited data. But nevertheless, now we have the situation that if you have a grid, which is a simple grid of 32 cube, you have about, 27,000 states and actions that you have to take, which makes it expensive. So instead, we thought of generating multiple agents that now the computational elements, they don't only solve the equations, but also they learn to complement the solution of the equation to achieve certain, global diagnostics. This is the multi-agent deep reinforcement learning to do turbulence. This is homogeneous turbulence. I'm showing you quickly some results. This is the state of the art, have been the purple and the green curves, and this is the energy spectrum. And now by doing this thing with our policy, we're able to get the energy spectrum much, much better than anything that existed before. And the last thing that I want to show you is that we are starting to move towards realistic numbers in predicting aircrafts and other bodies by going back to this wall model LES. And now we're learning the model using deep reinforcement learning. It's very important to take into account that we use particular physics in order to predict this model and to help the reinforcement learning algorithms. So this stage over here requires domain knowledge. But I think what we can do is we can train up to Reynolds number 10 to the 4. And now we're seeing that we can predict turbulent flows at a regime where airplanes are actually flying. So we see that there is some great success in taking multi-agent reinforcement learning and trying to replace heuristics. I'd like to close by leaving this thing up. This is from the book of Why by Judea Pearl, who is one of the pioneers of machine learning, who questions machine learning. And he says that machine learning is down here the same thing as what animals or robots may do, is to create associations. He considers a sign of intelligence when you intervene with a system, the same way actually what reinforcement learning does, and you learn by doing. And he considers, and I agree, that if we go about imagination, retrospection, and deep understanding, I think the human brain remains a fascinating barrier. We need to trust it. I think Colonel Tucker used the word trust this morning. I cannot emphasize it enough. I think that's what we need to build with these algorithms that we develop. And with that, I will thank you. I'll be happy to take any questions.
Thank you, Petros, for a great talk. We have room for maybe one or two questions, please.
Great talk, Petros. One question is about the reinforcement learning process you showed at the end. Does that mean what you're actually doing is changing the representation of your mesh at every time step because you're learning where to model with priority, or you're actually changing the model parameters? To me, it feels like you're changing the mesh, the computational mesh.
No, I don't change the mesh. The mesh is what it is, but I have agents dispersed inside the mesh, and these agents are complementing the numerics. They're fixing the numerical error that the method does, and they're bringing global knowledge, for example, about energy spectra or what other rewards you want to do. So in the end, all the computational elements, they're solving the equation, and they're learning to do other things. That is the idea.
Thank you.
Over there.
Roderick Pettigrew from Texas A&M. You started with a very practical problem, an example of detecting a rare circulating tumor cell using microfluidics to separate the cells out. And I recall this work from a Met toner that you referenced. The initial device was able to detect one circulating tumor cells in 1 billion normal cells. With your modeling and problem solving or artificial intelligence, maybe even inverse modeling, were you able to improve on that?
I have not done that inverse modeling on the device of Mehmet. What we did, actually, we were able to improve the original device by doing some kind of optimization. But these simulations are so expensive. That's actually one of the problems, that you cannot repeat them to do the design process. And then applying artificial intelligence techniques to these methods, I have not done that to be able to tell you something like that. So we still rely on the experiments of Mehmet. We try to help, but we are not there yet.
But did you learn something from your analysis? Or?
Oh, yes. I learned a lot about the uncertainty of my predictions because I learned of what is important in modeling when I model blood. For example, if you want to do very large calculations, people use the same viscosity inside and out for the blood cells, but this is wrong. And if you want to get realistic calculations about how blood behaves, you better take this into account. And then we had the experiments of Mehmet to tell us that if you model by following the physiological conditions, then you get better results and better matching with the experiments. But we are far from telling Mehmet, take this device and do that exactly, and then you will get a 10x to your experiment.
Great. We have to move on. I'm sorry, but Petros is around for the whole day, so please catch him for a coffee. Let's thank Petros again.